So the first day of class that we're going to be looking at statistics is with descriptive statistics, where our goal is going to be to have data that we're trying to then describe the data to an audience. So we're going to need some definitions to start off. The general idea of statistics is that it's the science of gathering, describing, and analyzing data. Population is a particular group of interest for a statistical study, and a sample is a subset of the population from which the information is collected. So the general idea here is if we could ask everybody a question, we'd love to. For instance, maybe I want to find the average height of a college student. If I want to find the average height of a college student, there is a real number out there, which is the truth. That real number, let's say, is 5'9". That the average, if I looked up every single college student, got out a tape measure, measured them tip to toe, and figured out each person's height, added them all together, and divided by however many millions of college students there are. The number exists. It's just not practical to actually go out and measure everyone. It's not even possible, probably. You'd have more people coming in before you got everybody measured. So even though the number exists, it's not a number we can actually know because it's not practical to really measure everyone. So instead, what we do is we use a sample. We determine that I think Manor is a good representative population of the larger college students. I'm going to take the 10 students who are in this room right now, measure their heights, average them, and say that I believe that is a good proxy for what the true average population height is. So the idea here is population is who we want to study if we could study everybody. Sample is who we actually can study in order to make inferences about the population. Let's say that the math department at Manor College is interested in what proportion of their incoming students complete a geometry class in high school. They ask 50 incoming students and find that 68% of them completed geometry in high school. What's the population of interest and what's the sample? So when we talk about the population of interest, the goal here for the population of interest is to say who do they want to study. The first sentence says, the math department at Manor College is interested in what proportion of their incoming students completed a geometry class in high school. So what the Manor College math department is trying to study is incoming students. The population of interest is incoming students to Manor College. 68% of the 50 students they asked had completed geometry in high school. The sample is those 50 students. In trying to determine what the larger group of all incoming students had done, we asked these 50. So what's the population of interest? Incoming students to Manor College. What's the sample? The 50 incoming students that we asked. The math department at Manor College is interested in what proportion of 2018 Pennsylvania high school graduates completed geometry in high school. They look at information from 5 randomly selected high schools in PA and find that 84% of the 2018 graduates from those high schools completed geometry in high school. Take a second, think about what you would say the population of interest is and what you would say the sample is. So in the first sentence, they say they're interested in what portion of 2018 Pennsylvania high school graduates completed geometry in high school. That means their population of interest is 2018 Pennsylvania high school graduates. When we talk about what the sample is, they look at information from 5 randomly selected high schools in PA and find that 84% of the 2018 graduates from those high schools completed geometry in high school. So the sample is all of the graduating students from these 5 high schools. So I would write it as all the students in the 5 randomly selected high schools, or all the graduating students in 5 randomly selected high schools. In this case, they haven't told us exactly what the number of people in the sample is, but that still describes what the sample is. When we talk about qualitative versus quantitative data, qualitative data consists of labels or descriptions of traits of the sample. Quantitative data consists of counts or measurements. The general idea here is that if it has a naturally occurring numerical scale, it fits as a quantitative piece of data. If it doesn't have a naturally occurring numerical scale and all I can do is group it with other things that are like it, then it would count as qualitative data. It's a little tricky in that you can't just go by does it have numbers or does it not have numbers, because there's certain problems where there's numbers involved, but they don't really have a natural scale. For instance, if you talked about phone numbers are qualitative, not quantitative, because all I can really do is say this phone number points me to that person. But there's not a naturally occurring scale where I would say the number 5552121 is somehow better than 5552120. That's why it would be qualitative, not quantitative. As opposed to earlier when I talked about heights, heights would be a quantitative piece of data. I could line everybody up once I'd measured them, put the smallest or the shortest person first, the tallest person last, have them in exact order in a numerical scale. I could know that this person is 3 inches taller than that person and make comparisons in that way. Quantitative data must be able to make those kind of comparisons in order to make sense. So a phone number does not do that. The phone numbers aren't really quantitative, they're qualitative data. So here's some examples of qualitative and quantitative data. Qualitative example would be the color of shirt somebody's wearing. I can put that into this person's wearing a red shirt, that person's wearing a yellow shirt. I wouldn't know how to compare them. The state that you live in, your favorite sports team, the type of food you had for lunch. In each of these instances, I could say which category you belong to, but I couldn't make comparisons between the categories. As opposed to quantitative data, shoe size, age, high school GPA, number of credits earned at manor, calories consumed at lunch. Any of those have a naturally occurring numerical scale where if two different people told me what their answer was, I could line them up and say this person goes there, that person goes here. So if I know that this person has a shoe size of 9 and that person has a shoe size of 10, I know that one person is one shoe size higher than the other. There's a scale underlying everything. I want you to now look at these 8 different variables and take a second to think whether they would be a piece of quantitative data or a piece of qualitative data. We start with the weights of babies. That would be quantitative. It's quantitative because I can put them on a scale. I can say this baby weighed 8 pounds 7 ounces, that baby weighed 8 pounds 3 ounces. I know where they are in relation to each other. For number 2, baby names, that would be qualitative data. I can say that this baby was named Charlotte, that baby was named Emily, but I can't put them in any order based on the names. Or any numerical order, I should say. Alphabetical order exists, but it's not really a numerical comparison. So again, number 2, baby names would be qualitative data. For hours in labor, there is a naturally occurring scale. This mother was in labor for 14 hours. That mother was in labor for 16 hours. I can take 30 mothers and line them up in order of how long they were in labor. So number 3 would be quantitative. Number 4 would also be quantitative. Price of balloons at the gift shop. At one gift shop, the balloons cost $3. At another gift shop, the balloons cost $3.50. Again, I could line everything up in a naturally occurring numerical scale. Number 5 is my trick question, hospital zip code. That's one where zip codes are numerical and that there's numbers in them. Uh, Once you have those numbers, though, you can't really make comparisons between them. Maybe at some point they had geographical underpinnings where you could say that 19002 was right next to 19003 and one was more west or east or something, but realistically, we've gotten to the point where zip codes have split and split again, and now they really just point you to where does the mail get delivered. It can't be compared. It's not like if I currently live in 19422, I'm really trying to get up to 19423. Again, they're just really markers as opposed to actual numbers that I can manipulate within a scale. The number of babies that the doctor has delivered, that would be quantitative. I could take all the doctors in the hospital and line them up based on who's delivered the most babies down to who's delivered the least babies. The type of medical insurance, number 7, that's qualitative. I could say that this person has Blue Cross Blue Shield, that person has Aetna, but I couldn't really make comparisons between the two in a numerical sense. Cost of hospital stay, I could make comparisons between quantitative data because I could say that this person paid $400 for their procedure. This other person paid $6,000, depending upon how long they had to be in the hospital. Those numbers are probably way low. I would guess that hospital stays cost way more than that, as I'm just trying to say them out loud, but the general idea is that I could make comparisons. There is an underlying scale. When you go to create a bar graph, these are the key things that you want to do. You want to determine what categories you're trying to display. Make sure that you properly label your axes. That's really the thing that I'm the biggest stickler about in my classes. If you don't have the labels on the axes, I always take points off for it. You want to make sure that the vertical axis is a count and it has the word frequency on there. The horizontal axis should list the different categories that things can fit in. When it says to choose a proper scale, really you want to base it on the largest frequency. You want to make sure that the upper bound includes that largest frequency. So if I'm asking people what their favorite fast food restaurant is, I ask 50 people and 30 of them say McDonald's, I want to make sure that that scale goes up to 30 or beyond. That said, you don't want to go too far beyond. It really wouldn't make sense if my highest number was 30 to have a scale that went up to 100. Then everything would just be compressed down at the bottom. It would be harder to see differences between the choices. For drawing and labeling the bars that make sense relative to each other, really what I tell students is we're going to do them by hand. We're going to learn to do them by hand, but you would always use a computer for this in modern days. Excel can do these great. You can just put in what the different counts are, pull down, insert bar graph, and boom, it makes the bar graph for you. So when I'm grading these for students, I care that the bars have labels and I care that they make relative sense. Like if one's 17 and the other's 15, I want the 17 to look higher. But other than that, I don't really worry about things being ruler perfect and measuring things out with lines because, again, I would strongly suggest that you would use a computer if you ever actually had to make a bar graph that you were going to present for a job that you were working. Here's some raw data from 50 people that I asked what their favorite sport was. 3 people said baseball, 15 people said basketball, 20 people said football, 2 said other, and 10 said soccer. I want you to use this raw data to try and create a bar graph. Make sure you label the axes and the categories. So I know there's not a ton of space here at the bottom on your Cornell notes. You might want to turn it over and do it on the back if you'd rather have a larger bar graph, or you can just try and write it small in that space. This is what it looks like in Excel. I will say that I would rather have it say frequency along the left-hand side there, so I apologize that I didn't have that written in. I also would probably want to put a title on this, like favorite sport, something that tells the audience, here's what we asked in order to get these responses. As you can see, each of these bars is separate from each other. They're not touching the original axis. They're all about the same width, and if I wanted to check what they go up to, I can see the properly labeled scale on the left-hand side that tells me the frequency. Here, my highest number was 20 from football. They have the graph go up to 25, which again looked reasonable to me. So anything that looks similar to this would be a good way to create this. I would say constructing a frequency distribution is the hardest thing we're going to get into today. It basically requires us to do some actual math with a calculator where we're trying to figure out different columns within the table as we display it. So the process itself is a little confusing the first time, but hopefully if we do one together, it'll make it so that you understand how we get the different column values and how we use the frequencies in the classes in order to create everything else. So the first thing that we're going to do is determine how many classes or categories we want in the distribution. That's really a choice up to the researcher. I would say that the books I use usually push 5 classes as the best way to get started. That's the number that's just kind of a generic number that I end up using. But in general, I would say that different books suggest anywhere from 4 to 10. It really matters, I should say. It's really determined by how many observations you have or how many data points you have. Then choose an appropriate class width. I can show you how to find that class width with a formula. You find the class limits. Those are going to be the first column in our table, and those class limits are going to determine how many of the observations fall into each of the different classes. Once we know how many fall into each class, we list that as the frequency, And with the class limits and the frequency, we can then calculate relative frequencies, cumulative frequencies, and midpoints. So let's say that we had this raw data set. This is before it's organized in any way. All we did was go to 20 different high school students and ask them how much they made per month at their part-time job. So after asking these students, we got this list of data points. First student made $200, then $800, $0, $500, $0, $1,000, $1,200, $500, $0, $300, $500, $200, $0, $1,500, $1,000, $600, $800, $0, $500, and $1,200. You can tell that I'm just kind of randomly saying numbers here where they're not in any order, they're just the order that I've asked people. It's always better when you're doing one of these frequency tables to organize. When you're determining the number of classes, really it's going to depend on what your data is. Typically between 5 and 20 classes in a frequency distribution, depending upon what you think will display the data most clearly. I would say if you have a huge data set, it makes more sense to have more classes. In general, in this class, when I teach it, I use smaller data sets, usually somewhere between 20 and 50 data points. And so I usually suggest that we use 5 classes as our number. So we're going to move forward with this example using the amount of money that students make at part-time jobs with 5 classes as our set number. Again, this is a choice that's made that's a little more intricate that I don't really think we need to go into for the purposes of this. So when you're choosing the class width, the formula that you want to use is largest value minus smallest value divided by the number of classes. For our data, the calculation would look like 1,500, the most that anyone said they made, minus 0, the least that anyone said they made, divided by 5. Those parentheses are important because we need to make sure that subtraction is done before the division. But when I do it for this data, I get 1,500 minus 0 divided by 5 equals 300. It's a nice round number, so it's a good thing to stick with as our class width. If it had been something like 289.4, we'd want to round that up to 300. I would say in general, you want to round to like a multiple of 10, a multiple of 5, a multiple of 100, something that gives you a nice clean number. When we want to find the class limits, you always start with the smallest number in the data set. So our smallest number is 0. We're going to set that as the lower class limit for the first class. Basically, in the top row of our table, on the left-hand side, we're going to write the number 0 in the first column. We're then going to add our class width to that. If we do 0 plus 300, that gets us to our new class width of 300. We add 300 again to get to our second class width, which is 600. We add 300 to get the class width to get to our third lower class limit, which is 600. Apologize. We add 300 again to get to 900, and we add 300 again to get to 1200. So we now have 5 classes, one that begins at 0, one that begins at 300, 600, 900, and 1200. We now need to do the upper class limits, or where each class ends. So to do that, we're just going to subtract 1 from where the class begins for the next class. Essentially here, we're assuming that anybody that gave us the amount of money they made at their job would do it in whole number values. It's possible that you would have people who are reporting decimals, dollars and cents, how much they made. If that were the case, I might want to go to 299.99 in my class limits. But for the sake of this data set, we're going to assume everything was reported in whole number increments. So that leaves us with lower and upper class limits that create the first class being from 0 to 229, or I'm sorry, 299, second class 300 to 599, third class 600 to 899, fourth class 900 to 1199, and the final class 1200 to 1500. Notice that the upper class limit is just our largest data point for that last class. Sometimes, depending upon how you've rounded the class width, that last class may look a little different than the ones that came before. So this is showing everything at once for how we're going to be determining what the class frequencies are. Basically, the raw data is written up here at the top of the slide, which reminds us what all the data points were that we began with. The idea was we asked 20 high school students, how much they made a month in a part-time job. We then are going to organize this raw data into the classes things fall into. So I want to read across the raw data and see how many of them fit into 0 to 299. I'd include this 200, this 0, this 0, this 0, this 200, this 0, and this 0. So in the end, that means I have 1, 2, 3, 4, 5 zeros and 1, 2, 200s. Notice that this 300 did not fall in the class. This 300 has to go in the new class that starts at 300. This is one of the reasons we always want to subtract 1 when we do the previous class ending point. If I had said this was 0 to 300 and the next class was 300 to 600, then this data point 300 would fall into both classes. We can never have it set up where a single data point goes into two different classes. That's why we had to subtract 1 to get this number 299. So when we go and count across and look for things that are 300 to 599, 500 counts, 500 counts, 300 counts, 500 counts, 600 does not count, and 500 counts. So that gives us 300, 500, 500, 500, 500. We do the same thing for the next class. We get 600, 800, and 800. For the fourth class, we get 2000s. And for the final class, we get 1200, 1200, 1500. Create the second column of the table, we're just putting in those frequencies next to the class limits. So the first column is going to be all the class limits. The second column is how many things fit into that class. So for the first class, we have 1, 2, 3, 4, 5, 6, 7 data points. That's why we say 7 is the number or the frequency that fell into the first class. There's 5 data points in the second class, there's 3 data points in the third class, 2 data points in the fourth class, and 3 data points in the final class. That sets us up for our table where the first column is the class limits, the second column is the frequencies we found. Using these two columns, we can now fill in the class midpoint, the relative frequency, and the cumulative frequency. Do the class midpoint, we're just going to take the two values that represent the lower and upper class limit, add them together, and divide by 2. So 0 plus 299 would give me 299. When I divide it by 2, I'd get 149.5. If I add 300 and 599, I'd get 899. Divided by 2 gives me 449.5. I keep doing that for each of the classes where I'm adding the two class endpoints, lower and upper, and dividing that answer by 2. If I then look at the fourth column relative frequency, the relative frequency should be either a decimal or a percentage. Here I've written them as percentages. Sometimes tables would prefer that you have them as decimals. So both of them are kind of acceptable. I prefer seeing it as a percentage because I think that's more familiar to most viewers. But basically all I'm doing is taking the total number of data points I had, 20, and taking the frequency divided by that to find the relative frequency. 7 divided by 20 gives me 0.35 or 35% of the 5 divided by 20 is 0.25 or 25%. 3 divided by 20 is 15%. 2 divided by 20 is 10%. And 3 divided by 20 is again 15%. We've now filled in the class midpoint and the relative frequency. The last column is the cumulative frequency. To do cumulative frequencies, what you do is you just take everything that's happened in that row or any row above. So for the first row, we have a frequency of 7. There's no rows above it, so we can just bring over that 7 as the cumulative frequency. For the second row, we have 5. That 5 needs to be added to all rows above. So 5 plus 7 is where I get the cumulative frequency of 12 in the second row. I can then add 3 plus 5 gives me 8, plus 7 gives me 15, or I can just see this as take the frequency in the new row, add it to the previous cumulative frequency. So 3 plus 12 gets me to 15. 2 plus 15 gets me to 17. And 3 plus 17 gets me to 20. I should always have the total number of data points as the cumulative frequency in the final row. This 20 does match the 20 total data points I started with, so I do feel like this cumulative frequency is correct. I now have my finalized table with class limits, frequencies, class midpoints, relative frequencies, and cumulative frequencies. If I want to create a histogram from this data, basically it looks a lot like a bar graph, just with a few key changes. Specifically, the changes include that the first bar should touch the vertical axis, or that starting axis on the left, and each subsequent bar should be touching the bar that came before. This is to represent that it really is an area between two numbers that's being shown by the bar, not a specific thing, so that you can kind of see how the bars interact with each other as you go along. Remember that this is always done with quantitative data, not qualitative. So whereas a bar graph has bars where the order doesn't really matter, they're just categories that give you information, in a histogram, the bar order does matter because the bar on the far left is actually closest in numerical value to the bar directly next to it. So the order of the bars tells you what falls into each class, but they also occur on a naturally occurring numerical scale. In order to do a histogram with this data, I want to be highlighting the frequency column. Let me go back. So I want to be highlighting the frequency column if I want to make if I want to make a frequency histogram. This would represent what my axis would be on my y-axis. I would say frequency, and I would label it based on just the raw frequencies. On the horizontal axis, I would label everything based on the class limits, or when I say everything, each of the bars would be labeled based on the class limits. If I want to do a relative frequency histogram, it would be the same idea. I would just change the vertical axis, and instead of giving raw frequency numbers, I would have it give relative frequencies. This is what the histogram looks like in Excel for frequency. So you can see that the highest frequency was 7. They had their scale go to 8. It's labeled as frequency on this left-hand side. The first bar that goes 0 to 299 is filled in here where it's touching the vertical axis. The second bar starts at 299, goes to 599. That's what's represented here. The third bar is 600 to 899, 900 to 1199, and 1200 to 1500. So this is what the histogram should look like in general. Again, I would always use a computer to do these. Excel is great with making histograms. But for the sake of what we're learning here, as long as your bars touch what they're supposed to touch, meaning the first bar touches that vertical axis, each subsequent bar touches each other, really just try and make them look about at the right height where they should be. The last thing we're going to do in this day one is we're going to look at the three measures of center: mean, median, and mode. The mean is the sum of all data values divided by the number of data values. So basically I add up the entire total and divide by how many data points that came from. Median is the middle value in an ordered array of data. In other words, I line up all the numbers from smallest to largest, and then I am going to take whichever one is in the exact middle, which I can find using a formula I'm about to show. For the mode, that would just be the value in the data set that occurs most frequently. Here's the general idea of the mean. I take each of my x values, I add them all together, and I divide by the total number of values. For the mean of this data set, 7, 8, 3, 9, 2, 3, 10, 6, I would add together 7 plus 8 plus 3 plus 9 plus 2 plus 6 plus 10 plus 6. That would give me a total of 48. I would then divide by 8 to get my answer of 6. One thing it's not really showing here is that there's understood parentheses around the 7 and the 6 here, just telling me I need to add everything on top before I do the division on bottom. For that same data set, we're now going to find the median. So it used to be written as 7, 8, 3, 9, 2, 3, 10, 6. Instead, we're going to rewrite that smallest to largest as 2, 3, sorry, let me go back, as 2, 3, 3, 6, 7, 8, 9, 10. Once I have it in order, I count how many data points I have. 1, 2, 3, 4, 5, 6, 7, 8. And then I use that number of data points in this position formula to find where the median is located in that ordered list. The position formula says I take n the number of data points plus 1 and divide it by 2. In this case, 8 plus 1 would give me 9, divided by 2 would be 4.5. With a position of 4.5, it means that I really need to average the fourth and fifth data point. So as I count over in my ordered list, 1, 2, 3, the fourth data point is 6, and the fifth data point is 7. When I say I need to average them, that means I need to add them together. 6 plus 7 gives me 13, and divide by 2. That's how I get a median of 6.5. Notice that 6.5 doesn't occur in the data set. The median does not need to occur in the data set. If you have an odd number of data points, it will be in the data set, the middle number, but whenever you have an even number, it'll be an average of the middle two data points. When I find the mode, really it's a lot easier if I use the ordered data set that I had from the median process. When I do that, I can see what the most common thing is. Here in my ordered data set, I can see that 3 occurs twice. That makes 3 the mode. If I had had another number occur twice, say this said 2, 3, 3, 6, 6 instead of 6, 7, I would report the mode as 3 and 6. That said, you don't just report the mode as anything that repeats. If there were 3 3s and 2 6s, 3 would be the mode and 6 would not be involved. The mode is the number that occurs the most frequently. Only when two things occur with the exact same frequency that's the most do you have a multimodal situation where you report both modes. I want you to find the mean, median, and mode of the following data sets on your own. Check with your classmates, see if you're getting the same things, but try and work through these data sets with the formulas provided.